So in the last lecture, we were talking about viscosity. When we talk about viscosity, it was considered as the resistance of movement of one layer over the adjacent layer. So there is some friction of the resistance being offered by one layer to other layer. To understand it technically, let me consider that there is a solid layer which is fixed. So this is fixed, so this will be having a velocity of 0. So u over here is the velocity, which is a generalized value of velocity. And there is some other plate which is parallel to our stationary plate, which is moving at a constant velocity of v under an action of force F. Please be clear, it is moving in velocity at a velocity v under an action of force F. So this is the condition, and these plates are filled with a fluid. And please remember that these are the very extremely long plates. So I am putting it with a dotted line, but they both go a long way on both sides. Now let us consider what is going on in here. So if we say that initially these both plates were stationary, the particles would have been stationary and would have aligned themselves in a single vertical line. Now if you consider that the top particle is in contact with the upper layer and the bottom particle is in contact with the bottom layer. So when the top layer will start moving at a constant velocity v, the top particle will also have moved a bit, and the bottom particle, the bottommost particle, would not have moved at all. So all the particles in between would have moved linearly, right? Because this particle would have moved less, this particle would have moved further less, and this is how the motion of the particle is. So let's put it in the form of lines. So if I draw it in form of lines, I would see that initially this was your condition, and later on the condition goes over here, right? So this particle over here is having velocity of 0, and this particle over here is having a velocity of v. Fine, we are clear up to here. Now let's look into something. If I consider that these both plates are having a linear distance or the vertical distance of L, so I would also say that this particle at the top has moved a distance of, how much would have moved? It's moved a distance of dA. Now if I ask you that what would be the value of dA, you can simply say that this is distance, and since this event would have occurred in a small time dt, so this can be written as v into dt, where dt is a movement in a very small time. So dA is clear to us, right? So let's keep it up there. The angle which it would have formed over here is, say, for a small time dt, the deformation was d beta. So this is a quite similar or a quite known formula, quite known value, which we call it a shear deformation. So dB is actually your d beta is actually your shear deformation. If I want to write d beta, I can write it as, how can I write it? I can write it as dA upon L. How can this be written? You can just understand that d beta is very small, and d beta can be written as tan d beta. So tan d beta is dA by L. Now further, I would replace dA with the values I have calculated over here. This is v dt by L. So over here, if I shift it to this side, so this is d beta upon dt is equal to v by L. So on the left hand side, what value do we have? This is called shear deformation rate, right? So shear means it's because of the shear stress acting or the shear force acting, and the deformation is d beta, and rate is divided by time. On the right hand side, we have velocity gradient. This is velocity divided by length. Let's hold it up to here, and I would mark this as my equation 1. Let's get back to our book. So if I say that for any height y in the fluid measured from the stationary plate, any height y in the fluid measured from the stationary plate, the system will have a velocity of u. So what I can write from here is that, so let me interfere something for you. So if I apply a similarity of triangle, these are the two triangles. This triangle is one, and this is the other triangle. So if I apply similarity of triangles, y upon u is actually equal to L upon v, right? So I can also write it u upon y is equal to v by L. U can be written as v y by L. Now if I want to find du upon dy. I want to check how the velocity is changing with respect to change in the distance. So I can find it v by L. Now this is our equation 2. So from 1 and 2 you can see that d beta upon dt is equal to v by L, and from equation 2 v by L is equal to du upon dy. So from here I can write that d beta upon dt is equal to du upon dy. So this what du upon dy shows us that how the velocity is changing with respect to a change in the layer distance between the layers. So this dy is actually distance between layers, and du is the change in velocity. Further, we know from the basics of mechanics that tau, which is the shear stress, is actually proportional to the rate of change of shear deformation. So this is d beta. So from this relation I can also say that tau is proportional to du upon dy, and from here if I remove the sign of proportionality I can write tau is equal to mu du upon dy. So finally I have a formula which I can write as tau is equal to mu du upon dy. This is called Newton's law of viscosity. Over here tau is shear stress, and since this is stress the unit will be Newton per meter square. Du is actually velocity or change in velocity. This can be written as meter per second, and dy is the distance between layers. This will be measured in meter, and mu over here is called viscosity, or we call it coefficient of viscosity, or we call it dynamic viscosity. We will talk about this specific viscosity term in the next lecture. So over here one thing is that this is change in velocity. Also I would like to highlight over here that the figure which we are using over here shows that the velocity profile over here is linear. In the further lecture we will understand this, that the velocity profile is not linear, it remains parabolic. For simplicity we have kept it linear over here.